Hello, this is for EMM3528 mechanical vibration. This is our video discussion for our assignment, which is to perform a vibration analysis on a cantilever beam. But before we start, let's introduce ourselves. My name is Rastgoo. My metric number is 195002.
My name is Megavharman and my metric number is 193499.
My name is Akmal bin Zuki. My matrix number is 192170.
My name is Kirubaanand A and my metric number is 194.
Okay, so I'm Afiq and my metric number is 177460.
All right, so this is our report. As mentioned, our group members, everyone is available here in this meeting. And so without further ado, we'll start with the introduction.
So for the introduction, basically we use beam for this experiment. So a beam is a slender horizontal structure member that resists lateral loads by bending, and this important element of engineering structures appears in various forms and compromises various certificates such as supporting members in high-rise buildings, railways, long-span bridges, flexible satellites, gun barrels, robot arms, and airplane wings. So basically, vibration analysis is also important for construction. It helps us to predict the behavior of the structure under different load distribution. In order to analyze the vibration of construction, we can use a cantilever beam instead of a construction itself. Therefore, the process of analyzing is simplified. So for our study, the free vibration of square cross-section aluminium are investigated analytically and also numerically under different boundary conditions. So analytical solution is carried out by using Euler-Bernoulli beam theory. For the analytical results that obtained from the experiment are compared with the numerical results from the FEM-based software called NCs.
I will take it from here, Mega, the theoretical background. For the theoretical background, from my research, I've actually found out there are two general vibrations, which of the of the amplitude. For general information for everyone, actually vibration doesn't theoretical because we always an effect which will be disturbing the release. The effect is actually the damping effect. And for the first vibration are vibrations where a continuous external disturbance or implementation of certain force is present to perform the vibrations of a system at a certain frequency. As every system object tends to vibrate at a specific frequency, which are also known as a natural frequency. At this point, when there is natural frequency, there will be a resonance effect. And for example of the resonance effect in our daily life, for further understanding is actually the mechanism of how a guitar works. The strings, when they vibrate, the hollow part of it, the sound will be actually amplifying the music that the person who is playing the guitar. So this principle is actually worked out by resonance. And for the general, for the for the simple example of damping situation, is actually the shock absorber for any vehicle. This shock absorber actually will be the damping device for particular vehicles. These are the basic examples that I can give for further explanation. So that's all for me.
So for the objectives, there are three objectives that we have to achieve. Firstly, we have to determine lateral vibration of beam for different lengths and initial conditions. Second, determine Young's modulus of cantilever material, and then we have to compare the experiment values lateral vibrations and Young modulus with expected values. Okay, next for the magnification factor. As you can see in the report, magnification factor of a system is defined as the ratio of vibrating systems when the force frequency approach to the resonance frequency of a vibrating system.
So for the methodology part, I'm going to explain about how the flowchart of the project works actually. As we can see over here, it starts from the group formation and also the group formation of all P5 and discussion and also some task divisions on which part we are going to take about, for example, like on theoretical background. And so we had set some timeline for submission and also shared weekly updates on the WhatsApp group on whatever things that we actually just share it in the WhatsApp group, and we just abstract some information through that sharing. And also we have progressed to the report and completed the report by the timeline fixed. And also we submitted the report. And now we are doing the video recording for our report presentation. And furthermore, we will be doing the video submission on a perfect time.
Moving on to the experimental procedure, this experiment was not able to be done in person, especially in the UPM, given our pandemic COVID-19. So I've referred to the paper published in the International Journal of Mechanics and Applications by Mehmet Afka from the Süleyman Demirel University in Turkey. So according to Mehmet, he has devised the experiment and as shown in the diagram. So basically, the experiment requires the usage of 3 differently cross-section aluminum bars with an equal length of 3.250 meter, but their cross-section areas differ, given with the A1 equivalent to 0.0225 meter squared, A2 is 0.04 meter squared, and A3 0.0625 meter squared respectively. So the experiment is done by attaching the beam on a support system to ensure that it is in the form of cantilever, and then it was given an initial displacement at the very end of the beam by pushing down the beam by hand. The results we've obtained can be split into 2 halves. Firstly is the FEM based software, that is the ANSYS. I believe it's in release 14, and the other is analytical natural frequency analysis, which is done using numerical method as stated previously in the, I believe, in the background. Now moving on to the FM based software versus analytical natural frequency analysis. As you can see in the diagram, these are all the results posted from the different lengths and cross-sectional areas of the aluminum bars. Okay, so the third part of the experiment is the effect on beam length on natural frequency. So basically this part is where we observe how would the length of the beam affect the natural frequency of the system. From here we can see that the change in length does have a constant effect on its natural frequencies for various boundary conditions. These boundary conditions given are the cross-sectional areas of the beams. Okay, 7.4, we study the effect of cross-section beam area on its natural frequency. From the diagram shown here, it can be concluded that the change in cross-sectional area of the beam has a constant effect on the natural frequencies of the beam for various boundary conditions and length, which I've stated earlier. And lastly, the determination of Young's modulus of the beam. This is done based using calculation method, and we've reached a value of 70 times 10 to the power of 9 Newton per meter squared, which is consistent with the value given by normal aluminum or an alloy of it.
So the first section of the discussion, let's very briefly describe the results. I think it's good at this point to remember the main objective of this whole assignment. We wanted to analyze vibration, and we wanted to analyze the vibration of a cantilever beam and ultimately find the Young's modulus. In order to accomplish this, of course, we use both FEM and numerical analysis. When using FEM, we try to use simulations. When I say we, of course, the journal provided us that we use FEM as the main source of trying to conduct the experiment. So when we go through the results, the first graph of the results which we found, we were able to conclude that natural frequencies were increased with the growth of mode numbers. Intriguingly, the next figure in the results concluded us and basically gave us that natural frequencies decrease with an increase in length. So length and mode numbers actually have an opposite reaction, opposite effect on the cantilever, on the natural frequencies. But when we conducted this experiment, the cross-sectional area was similar for the different beams that we conducted it on. For the next experiment that we did, this time the length was equal for all of the specimen, but the cross-sectional area was changed. When we did this, when we did this change, we found out that the natural frequency actually arise with the increasement of the cross-sectional area. So the three factors that affect the natural frequencies are the mode numbers, the length, and the cross-sectional area. The mode numbers increase and the natural frequency increases. The length, when the length increases, the natural frequency actually decreases. When the cross-sectional increases, the natural frequency also increases. So these were the very general results that we were able to get from the experiment. And of course, with all of these factors now in mind and with the values that were obtained, we were finally able to use the Bernoulli method to find Young's modulus. So let's go to some of the errors and uncertainties. Now, of course, since we're using FEM and numerical methods, there is not much in terms of errors. Unfortunately, we could not do this manually. If we were to do this manually, I think human error would be one of the main factors that would affect this project. But again, since this is a very basic and fundamental experiment and it's already been done before, it's kind of safe to assume that the results obtained from the FEM analysis are around 100% accurate. It's not exactly perfect, but it's very close to what we would expect. So in terms of recommendations, of course, we use FEM analysis, as we mentioned before. However, there are other numerous methods that we can use to conduct this experiment. One of the very intriguing articles that I found was, of course, using MATLAB. MATLAB, of course, the base source for MATLAB is coding. So by coding and making block diagrams, we can actually conduct this experiment using codes. It's a different method, but the results are, in the end, the same. If we want to go and to have a more precise and accurate results, we could use computational mechanics. Now, these mechanics are actually very complex analyzing methods with great detail in terms of results. But of course, they require high understanding as well, which I think it's a little bit above our understanding. It requires a lot of training and practice. And of course, the more natural way, we could actually find all of these using equations of motion, which we've learned in our class. We can definitely determine the natural frequencies and the mode shapes of a multiple degree of freedom system using the eigenvalue problem. That is all in terms of the recommendation. We can use numerous methods, of course, manually in a lab. That's one of the ways, but unfortunately, we could not do this in the lab. So we relied mostly on softwares. If we wanted to do this manually ourselves, the other option would be to use this using the equations of motion. That would be all for the discussion.
Lastly, for the conclusion, okay. So all the objectives are achieved. The Young's modulus of the cantilever material and the lateral vibration of beam for different lengths and initial conditions were successfully determined from the experiment. And the experiment value, lateral vibrations and Young's modulus with expected values were also compared at the end of the experiment.
All right, then I guess that is all from us. Thank you, doctors, for listening. That is all. Thank you very much.